Atomic absorption spectroscopy is another option. In this case, we record photons that are absorbed by atoms. So what happens to our sodium atom? The only player, again, is 3s1 electron. And as we seen before, most of it will sit at 3s orbital. If photon with energy that is exactly equal to difference between this level and this level will collide with atom, this photon will be absorbed and our 3s electron will jump on upper level. It is possible to send it to 3p orbital or to 4p orbital. It is impossible to send it from 3s to 4s or from 3s to 3d because of symmetry rules. Physicists can explain them to you. So we'll have two possible absorption lines here that are yellow and two others at 330 nanometers and several other above. Now, as we have seen before, most of sodium will be at ground state and zero. Very small number will be at higher state. The same will be true for all other elements. Now we do not need to have electrons at upper level. What is sufficient is to have our atoms in atomic state, not as molecule, but as atoms. So now our acetylene air or acetylene N2O gas mixture can give us flame that will produce atoms. Let's look at what happens in this flame. So first, we have our MX from sample coming into aerosol. Okay, in our case metal was sodium, so let's say it was sodium chloride. Sodium chloride dissolve in water, make small droplets of aerosol. When these droplets are coming into dry air, they are making small particles of sodium chloride, very small, because we have very little sodium chloride in our aerosol, so resulting particles will be very small. Next, at high temperature, these small particles will evaporate to make sodium chloride gas. It will be very high temperature. And of course, this gas can absorb light, making excited molecule. And in turn, they can emit. It's very improbable for sodium chloride, but still possible. Now, next step will be crushing chemical bond, making atom of sodium. Because this is gas phase, this will be main component of our flame. And of course, chlorine as well. This is what we want. Our sodium atom can absorb photon to become excited and then can emit fluorescent photon, as a matter of fact, or can relax back to ground state by collisions. Now, what kind of side processes are possible? Our sodium can ionize, making A plus Na plus in our case, plus electron. This is very unfortunate because ions will have different spectrum than atoms. Atoms can also react with oxygen atoms in flame. Flame is oxygen containing, so it can make metal oxide and metal hydroxide. These are molecules and they can absorb and emit light. We do not want this to happen, and we do not want this to happen. What can be done to avoid formation of molecules? You need to increase temperature. If you have very high temperature, then all molecules will decompose into atoms. Unfortunately, the same increase of temperature will result in higher dissociation of our sodium. So we need to balance these processes. We can suppress ionization adding electrons to our mixture. How we can do that? We can do other elements, say potassium, that will make ions and electrons, and these electrons will react with our sodium ions, making back sodium atoms. It's a complex procedure, but this can be done. So as a result, we have sodium atoms in our flame. Same process will be true for any other metal of periodic table. Non-metals are more difficult to handle, and in most cases it's simply impossible. Now, next step, how we can produce absorption. The easiest way would be to have very strong lamp and make very narrow band of light. This would be crazy expensive. First, monochromator that will give us very narrow band of light will be very expensive. Next, this source that will give us that many photons will be very expensive as well. The solution was very interesting, difficult. Instead of making very narrow monochromator, we are using special lamp, so-called hollow cathode lamp. What is this? This lamp has two electrodes. One is anode, another is cathode. On cathode, we are placing our metal. In our specific case, it was sodium. So at high temperature, it will evaporate. Electrons coming from anode to cathode will collide with these atoms, and they will produce light that will be exactly the same as we need. Photons will have exactly the same energy that is coming from transition from 3p to 3s, or vice versa, from 3s to 3p. So for each element, we have specific lamp that produces spectral lines specific for this very element. Next, the role of our monochromator is only to select this line. Our monochromator can be of relatively poor quality and still can select the line out of number of other lines. It does not show us real spectrum, but it works as wavelength selector. So, to have specific wavelengths, we need two tools. One is source, that will be lamp specific to element. And next, monochromator. So what happens? We have our emission spectrum of source. It has several different lines, and we need only one line. Other lines can come from our sodium or from neon gas that is in lamp or from any impurities. Next, our monochromator of wide bandwidth selects the line we need. These photons are absorbed by our flame, so we have exactly the same picture as with usual absorption spectrum. Absorbance is decimal log of P0 to P. So that is large P0, and that is much smaller P after absorption. So we have a usual absorbance, and that means we have Beck's law. Now, the design of the object. Our sample is coming through the capillary into nebulizer. Nebulizer means we are making nebula, fog in Latin. So this fog or aerosol is mixed with fuel and oxidant. Whatever larger droplets are going back to waste, and this mixture evaporates and come into burner head. We do not want to use 1 centimeter cuvette. We are using burner head that allows us to have flame along our beam. So we'll direct beam along the burner head, and length of our flame will be not 1 centimeter, but perhaps 15 centimeters or something. Alternatively, we can atomize without flame. What's the advantage? In flame you have oxygen, so you are making oxide molecules. If you atomize your sample without oxygens in noble gas, say in argon, you will have far less molecular peaks. So what can be done? You put your sample in a graphite tube, we name it sometimes graphite cuvette or graphite furnace, and then we start heating it. How can we heat it? Graphite conducts electricity, and it can sustain temperature all the way to 3000. So when current is going around this tube, it hits very quickly because your sample and the tube are very small, and you quickly reach high temperature. So at first step, after you introduce your sample, how much you introduce? Say 10 microliters, not more. So it's much less than 1 drop. First you dry it at 100 Celsius. It will take a couple of seconds. Second step, you increase temperature to 400 and run decomposition. You may increase it slightly higher at the end of this process to assure that all chemical compounds are gone. You have only atoms. Next, you quickly raise temperature to 2000 degrees or around that. So your target elements are atoms in gas, not in solid, but in gas now, sitting here. At this moment, a beam of light is coming through the cuvette along it and is absorbed you are measuring absorbance. After measurement is done, and it takes 1, 2, 3, 4 seconds, no more, you are cleaning your cuvette by increasing temperature all the way to 2400 degrees. So everything is flushed out by stream of hot gas, and then you cool the system down. After around 40-50 seconds, the cuvette is ready for injection of the next sample. Tube is not very simple device. It has several improvements that helps vaporization of the sample. So we have several different methods. We can look at them and compare how good they are. So for example, for nickel, very common element, if you have inductively coupled plasma with atomic emission, you can get this detection limit. If you have better nebulizer, you can go lower. With graphite furnace, you can go much lower, but this method will require some additional training, and you cannot do simultaneously several elements or metals. You can go even further with ICP mass spec, but that's a separate story. So what elements can be done with atomic spectroscopy? Practically everything. Well, you cannot do noble gases. You cannot do non-metals. Detection limits for carbon, nitrogen, oxygen, fluorine, chlorine, sulfur are very poor. So you would not want to do bromine or iodine. Otherwise, everything is possible to do. At left side, elements that are better analyzed by emission. Some elements require very high temperature and usually analyzed by ICP, inductively coupled plasma. What about simplicity and cost of methods? Flame absorption is the cheapest method. You can buy an instrument for very reasonable price. It doesn't require much training to operate. But your detection limits will be relatively large. Precision is not bad. You have no more than 1% error. Spectral interferences are very few, but there's lots of difficulties with chemical interferences if you have a complex sample. If you run furnace, graphite furnace atomic absorption, you can go for much lower detection limits. Precision is visibly worse. Obviously, if you are using very small sample, it's difficult to work. You have lots of interferences, but they can be overcome. What's interesting that because of very high temperature, you can use slurries and solid. The instrument will be far more expensive, but sample volume will be very small. With inductively coupled plasma, you have relatively low detection limits, much better with flame absorption, but not as good as with furnace. You have very large range in which you have linear calibration. It goes all the way to 100,000 fold. You have very good precision, better than with furnace absorption, but you have very many difficulties with very complex spectra. On the other hand, you have very few chemical difficulties. The instrument will be roughly 5 to 10 times more expensive than flame atomic absorption instrument. So people select the instrument which suit their problem, and in modern industry you can see all of these methods working.